It's good to speaking after Jan, so I will recover some of the subjects he talked to and talk about the other research we're developing in our group. Well, essentially a long-range interaction system, which the main characteristic of it is the fact that energy is non-additive. Because if you, for instance here, you consider an interaction which decays like a power law, like 1 over r to alpha, and you compute the whole potential energy on a sphere of radius r, you take just a small portion of radius epsilon here near the particle, due to avoid the divergence at 0 distance, you see that the whole potential energy, in fact, diverges if the power of alpha is smaller than the spatial dimension. That means if you cut your system in two, the interaction energy between the two parts is as important as the core energy. So you cannot, the system is not divisible. So you cut the system in two and you separate the two parts. The interaction energy is as important as the energy within each part. So this brings a lot of consequences. I will talk about some of them here. We have some examples of this, as Jan told. We have interactions among galaxies. Here we have a globular cluster. The number of particles is very important here because, as he just said, the time you take to reach equilibrium depends strongly on this number of particles. Other examples of system with long-range interactions here is the interactions between vortices in two-dimensional turbulence. So you can model the interactions among these vortices using a logarithmic potential, which you can consider as long range also. In other simplified models, like, well, you have charged plasmas, of course, unshielded Coulomb interaction. You have wave-particle interactions in plasma, which is a real lab model. In some simplified models, the spin models, I will talk to two of them here, the Ringer model, the Hamiltonian Field model, which is the XY model Jan spoke before me, gravity in two-dimensional, one-dimensional gravity interact, and so in small systems, when the size of the system is of the order of the range of the interaction, that they can, in some sense, behave like similar to those long-range interacting systems. Those systems, they can have quite some different characteristics. They present, not always. Some of them, like, as I said, they are non-additive. Energy is non-additive. This has some interesting physical consequences. This can lead to ensemble inequivalence. I will give you equilibrium inequivalence, ensemble inequivalence. I will give an example just now. Negative heat capacity, which does not violate the second law of thermodynamics. I will explain why it does not. We can have non-Gaussian stationary states out of equilibrium, because if you go to the thermodynamic limit, you never reach equilibrium, and your system relaxes to a stationary state which is non-Gaussian, in fact, and stay there forever. And if the number of particles is infinite, we can have anomalous diffusion and anergodicity also. So we can speak of the dynamical evolution of the system in three different stages. A first stage, which we call a violent relaxation. We saw this in Jan's animations. The system rapidly relaxes to a quasi-stationary state with damping oscillations. And it stays in this quasi-stationary state for a very long time, and it relaxes to equilibrium due to collisional corrections in the dynamics. If these collisional effects, they vanish if you go to the thermodynamic limit. So the larger the number of particles, the longer the time it takes to reach equilibrium. And the last stage, if the number of particles is finite, you reach equilibrium, but this can take a very, very large time. For instance, if you consider a galaxy with tens or hundreds of billions of stars, the time it requires to reach equilibrium is some orders of magnitude larger than the age of the universe. But if you consider just a small globular cluster with tens of thousands of stars, then the time it takes to reach equilibrium has already been passed. So most globular clusters have a Gaussian velocity distribution. So it depends on the size of your system, if you, of course. To discuss some issues I want to present here, we consider some simplified models. Well, the first one is the so-called self-gravitating ring model, where you simply take particles constrained to move on a circle, and the interaction is gravitational, so a potential like 1 over r. So the distance is given by between two particles by 1 minus the difference of the cosine of the angle position coordinate. And with the judicious choice of units, we can write the Hamiltonian in this way. But first here, we have this plus epsilon that is usually a small parameter to avoid the zero distance divergence. And we have also this factor 1 over n. Well, we can introduce it by a change in time units. This is valid as long as n is finite, of course. And we have a kinetic energy term. So this is the coordinates are theta and p, which is conjugate to theta, which is an angular momentum. And we have, well, you can choose the units, mass units, and so on. Yes? Well, the time to reach equilibrium, in this case it depends, since it's one-dimensional. If the state is homogeneous, it goes like n squared. If it's inhomogeneous, it's like n. But no, you can reach equilibrium. So you're not changing anything to that time by doing this rescaling. You're not setting it to 0 or 50. No. As long as, this is a usual rescaling, but in the literature. But as long as n is finite, it's just a rescaling of time. This is very useful to compare, let's say, simulation with different n. But you can do you can consider without this factor. It's called a Katz factor, and it has the advantage that now the energy is proportional to n, because here I have n terms, here I have, it's proportional to n squared terms, and I divide by n, so the whole energy is proportional to n. It's extensive, but non-additive yet. Well, the other model, if you forget that epsilon is small, you make it bigger, and you take just the first term in a Taylor expansion. I have what I call the Hamiltonian mean field model, which is Hamiltonian, which is the XY model Jan talked earlier, before me. Okay. So again, we have here the kinetic energy term and a potential interaction. All particles interact with the same intensity through this cosine potential. This model is very studied in literature because first it's solvable at equilibrium. So I can define the analogy of the analogous of a magnetization as the average of the cosines and the sines, the two components of a magnetization, like this. And the equilibrium distribution function is given by this expression here, where the magnetization is solved by this equation, where here is the Bessel functions with index 1 and 0. Beta is the usual inverse temperature. And the other advantage, if you do a simulation, is that to compute the force on particle I, we have to know the two components of the magnetization, given by this expression, and we have the force. So to compute each component, it takes n computations. So the numerical effort to simulate an n-particle system is proportional to n, while for this model, it is proportional to n squared. So here I can simulate tens of thousands of particles. Here, for the Hamiltonian mean field model, I can simulate tens or hundreds of millions. So the reason why it's very good to use it as a toy model to study some properties of long-range interactions. And finally, the other model is the two-dimensional self-gravitating particles, where the potential, again with the same Katz factor, is given by this expression, and here a small epsilon, again to avoid divergences at zero distance. And the logarithmic potentials came from the solution of the Poisson equation in 2 dimensions. Okay? In an equilibrium, if you have a very large number of particles, then your dynamics is described by the Vlasov equation. If the number of particles is finite, then instead of this expression being equal to 0, you have a collisional term, like in Landau or Balescu Lenard equation, which gives essentially the scaling of this time to relax to equilibrium. But since the Vlasov equation is reversible, you don't have evolution to equilibrium. You can relax to eventually a possible quasi-stationary state, but never to a Boltzmann Gaussian equilibrium distribution. So here we have the mean field force, which is minus the gradient of the mean field potential, which is the average of the potential at position r due to all other particles. Here's just a simulation of the solution, numerical solution of the Vlasov equation, a code in 1 dimension. This was performed using, as all other numerical simulations, which I will present, they're performing on graphic processing units, graphic cards, which accelerates a lot of these computations you can do on a normal desktop computer at very low cost. So this is an example of what we call a water bag initial condition. Here in the horizontal line is the theta, the angle theta, and here the momentum, the conjugate angular momentum, for a uniform distribution. In this interval, this is solved on a numerical grid, like 2,000 by 2,000 points, and we evolve in time 0, 10, 100, 200, 300, 1,000, and we see this structure, this filamentation structure being formed. The area of this figure is preserved. This is a characteristic of the Vlasov equation due to the Casimir invariance. So, but this filamentation goes being formed it goes around this the core here, and finally we lose the resolution of the grid, and we see again, as Jan told us, this core halo structure. So, and you stay. This is a quasi-stationary state. You stay there for an infinite long time if you are in the thermodynamic limit. Otherwise, if n is finite, you relax very, very slowly to equilibrium. Here, just to illustrate what happens also in something interesting in this system for the ring model, not the HMF model. This is the caloric curve for the model. This is temperature as a function of energy per particle. We can obtain this curve in many ways. For instance, since I know that for large n, correlations are negligible in this, interparticle correlations are negligible, I can maximize the entropy numerically and obtain this curve, which is the continuous line, the variational method. I can use Monte Carlo and simulations. In fact, on the left here, these are micro-canonical Monte Carlo, fixed energy. I can do this on the computer, which reproduce exactly the line obtained for maximizing the entropy. And curiously, we see here that we have a region of negative heat capacity. So this, the red diamond points were obtained using a molecular dynamic simulation with 1,024 particles. I mean, solving Hamiltonian equations of motion for the system, for the n-particle system, and waiting for a very long time until it reaches thermodynamic equilibrium. So each of these points takes like a day on a parallel implementation. So it took 2 weeks to do this graphic. And it reproduces quite well the results from Monte Carlo and this variational method from first principles. There are no assumption at all. Just solve the Hamiltonian equations of motion. And this is microcanonical ensemble. Then we can do something similar for the canonical ensemble. I can do a Monte Carlo simulation. Here, the complete curve in continuous line is just a reproduction of the microcanonical curve. But how can I say? Here I have canonic Monte Carlo simulations and the minimization of the free energy, which can be computed from the entropy, also by a Legendre transformation. In all these cases, there's a gap in the energy. In fact, I don't show it here, but I can also reproduce from molecular dynamic simulations the same graphics. I can build a bath of particles, very large numbers, and simulate everything with solving Hamiltonian equations, and we have the same results. When you arrive at the phase transition, where you should normally have the Maxwell construction, which is this dotted line. Normally, in short-range interacting systems, this line here would correspond to phase coexistence. But since energy is non-additive, and therefore entropy is non-additive also in this case, because the system is not divisible. So there is no phase coexistence, and your system simply jumps from here to here. This whole energy interval is physically inaccessible. You cannot realize a system in this state. And we can show so by numerical simulation. I did this, I'm not showing now, but later I can show if you want. If you put your system here in this state, and then you couple your system to the bath, well, it simply will evolve out of these states up to the corresponding state which minimizes the free energy. But you cannot have phase coexistence, because phase coexistence means that you have one part of the system in one phase, and another part in another phase, then you add both parts. Then this adding of the parts is not possible if the interactions are long-ranged. And negative heat capacity, this is a slide I always like to present. It doesn't violate the second law because what is the usual argument to prove that heat capacity must be positive? Well, in the canonical ensemble, it's a simple calculation to show that heat capacity is always positive. But in the microcanonical ensemble, how you prove it? The argument goes as follows. You take a system and you divide it in two parts of the systems. You have an energy E1 here, E2 here. Then if you have a difference in temperature, then heat flows from hotter to colder in this direction. And if the heat capacity is negative, then the hotter becomes hotter and the colder becomes colder, and you have a runaway effect and the system is unstable. It fails for long-range systems, this argument, because here I'm saying I have an energy here, E1, and an energy here, E2. I'm supposing that the interaction energy and it's just an interface energy which is negligible with respect to the energy of each part, which is not the case, again, if the interaction is long range. So this argument is not valid. So this is why you can have negative heat capacity. In fact, the positivity of heat capacity comes from the second law and the additivity of the energy. You need both. In this case, I don't have additivity. But I have the second law, still valid, of course. Here's an example of what I said before. If I prepare the system here, in the microcanonical ensemble, it is a region where the heat capacity is negative. Then I couple it to the bath and let it evolve. I see the result is here. In black and red are the temperature of the ring model and the temperature of the bath. They stay the same. Here's the kurtosis, which is essentially the reduced fourth moment of the velocity, which for a Gaussian is always 3. So we have some oscillation, but it stays always around 3, which means that during the time evolution, the system has a Gaussian distribution. But the interaction energy of the potential energy of the ring model, it goes to a smaller value. That means your system is losing energy. So I start in this point, and I go to this point. It gives energy to the bus, and this point corresponds to the minimum of the free energy. So the system, this point, which is stable in the microcanonical ensemble, is unstable in the canonical one. So they are both different. And all these results are just obtained from solving the Hamiltonian equations of motion. Okay? So I will, before I continue, I will discuss some. I have this problem. What happens, like in the HMF model, if I have periodically bounded conditions? And I will come back to the symmetry breaking of Jan. Like here, for instance, I have two particles. Suppose they have the same velocity. And if you traverse at one of the edges, you reappear at the other edge. Here, your center of mass is here. But since this particle is closer to the edge than the other one, it traverses before the particle at the left, and you come to this situation. Then the center of mass, which was here, moved to here. Okay? This is just an ambiguity of defining a center of mass in periodic boundary conditions. You have a total vanishing momentum, but still your center of mass jumped. It doesn't move continuously, it just jumps. And consider here, this is the equilibrium distribution function for the HMF model in a non-homogeneous state, from minus pi to plus pi. It's small here at theta equal pi, but not exactly 0. It has a finite value. So there's a probability that you have a particle here at the edge. So I can compute what is the probability that one particle traverses at the edge at theta equal pi in a given time per unit of time. I can compute this given by a Poisson distribution, in fact, given here. And this probability P here is the probability that any one particle traverses the boundary in an interval of time delta t. You can compute in this way. Here's the equilibrium distribution function, which for the HMF model is known, and we obtain this result for a small delta t. So the probability that a number of k of particles traverses at one of the edges at plus pi or minus pi, they are the same, is given by this. And then I can compute what is the probability that the difference of particles traversing from one side and the other side is k, because I can have the number of particles that traverse by units of time can fluctuate because I have a finite number of particles. And it's given by this distribution, which is known as Kellam distribution. It's a distribution of the difference of two Poissonian variables. Well, this means that you have a finite probability that you have a net flux of particles at the edge. And you have this, your center of mass can jump. In fact, this is the theoretical distribution. This is obtained by a simulation. I will have to jump in some details. Here's a graph of a simulation of 10,000 particles for the HMF model of the position of center of mass. It has some discrete jumps because every time one particle traverses there, your center of mass has a very small movement. But the point is, interparticle correlations are negligible here, but autocorrelation of the position and velocity is not negligible. It's important here. So once you traverse one particle, there's a bigger chance that the next particle that will traverse is in the same sense. So it creates a net motion of the center, an effective motion of the center of mass that we can see in a very large scale, here up to 10 to 6 in a simulation. It's a diffusive motion. In fact, super diffusive motion. Here I will show what happens if I do this a simulation. And the importance is that the total angular momentum here is 0. Here I have theta, and here's the angular momentum. And the error is a fourth order symplectic integrator. So it is very well preserved, the momentum. And this is what happens. It simply starts to rotate, to move. In fact, if the center of mass, it can go in one direction, then reverse, then go back. And if you do the statistics of that, you'll see it's a diffusive motion. You can, which starts as super diffusive. We can compute this from the diffusion of individual particles. Let me accelerate it a little bit because time is short. You see? Then it stops, oscillates, goes back in the other direction. Let me show. Oops. Stop. Oops. So here are the X and Y components of the magnetization, which essentially gives the position of center of mass. It shows, in black is the total magnetization, which is constant because I'm at equilibrium. But you have a symmetry breaking around the circle. So we see that this movement goes up to the time of 10 to 6, 10,000 particles. Here is 1 million particles. The total time here is 10 to 7. If the number of particles augments, then this movement diminishes. And if n goes to infinity, it stops, because there are no more oscillations at the borders. So yes, angular momentum is always conserved here. Yeah, they compensate always, of course. But the net effect, you see the bulk, the position of the center of mass, it's really moving. Because you have an ambiguity in the finite center of mass if you have periodic boundary conditions. If the conditions are not periodic, so you go to minus to plus infinity, you don't see that. Periodic boundary conditions are a necessary condition to this to happen. Now here is for two-dimensional gravity. So I have 10,000, 2,400 particles, initially at rest on the ring, uniformly distributed. Of course, there are microscopic inhomogeneities that get amplified by the oscillation in the dynamics. And we'll have a symmetry breaking also here. The violent relaxation first, very fast, and we see there's a bar structure formed. That suddenly wants to rotate at 0 angular momentum. It's the same effect, in fact. You can see this with two coordinates, an radial coordinate r and an angular coordinate. So we have a boundary condition in one of the coordinates. So the same effect plays here. If you follow the whole simulation, you see that this bar structure slowly relaxes due to collisional effects. Here, at least in this simulation, is clearly visible. But let me accelerate it a little bit. And again, you have a diffusion in angles, diffusion process. Okay, what I have here, in fact, I have a Goldstone mode, classical, in classical mechanics. it rotates. You have the symmetry breaking in a periodic direction. So I have an infinity number of equilibrium or non-equilibrium states, and the energy cost to go to one to the other, it's 0. So you can excite these modes by thermal fluctuations. And due to boundary conditions, you can have an effective motion of the center of mass. And just to go a little bit, this is the diffusion motion for the HMF model. It's super diffusive, then it goes to normal. I will jump this just to finish 2 minutes. Okay. Here's the largest Lyapunov exponent for the HMF model as a function of energy per particle in the non-homogeneous phase. And we have here at low energies, this exponent, Lyapunov exponent is positive, but small, then it gets much bigger. And the reason is because here's the amplitude of the distribution function at the edge of the boundary. If you center the equilibrium at θ equals 0 and you look at the probability of having a particle at θ equals pi, it goes like this. So when this probability is considerable, these soft modes, these Goldstone modes, get excited by fluctuations. And then you couple the motion of each particle, which obeys essentially the equation of motion of a pendulum, you couple it to this Goldstone mode, and it enhances chaos, the large Lyapunov exponent, which you can see here. And you have what we call a transition from weak to strong chaos. This is the kind. Well, don't have time. There's conclusions. So we have very symmetry breaking can be associated to a Goldstone mode in this case, and you have periodic boundary condition. These Goldstone modes interact with the motion of the particle, enhancing chaos in this case. And this can have some consequences, I think, in many. For instance, if you think the structure in galaxies, how they move, or globular clusters, in chaos in the systems too, which we are trying to investigate it now. So, thank you.